I'm back from paternity leave. So today's tutorial is all about Fourier series and how to calculate them. So we'll be doing some questions whereby we are asked to calculate a Fourier series, and then we're also asked to discuss some of the properties of the Fourier series. For example, sketch the curve of the function that the Fourier series converges to. So my plan is to do 184 and 185. Okay, so before we get down to business, what is a Fourier series? Well, I'm glad you asked. Now, you don't have this in front of you, but and don't worry about copying all this down. A Fourier series is just a series that involves cosines and sines. And to compute the Fourier series of a given function, you calculate these coefficients, the a naughts, the a n's, and the b n's. And you do that using integration. Now, the types of functions, f of x, that we'll be looking at have a few properties. Firstly, they are what's known as piecewise continuous and have a piecewise continuous derivative. And when I draw a few graphs, you'll get a good visual understanding for that. Furthermore, the functions we're going to look at are periodic with period 2L, where L is some positive number. Now you can see in the formulae here, this L pops up. So L's half the period of our given function. Now, like I said before, to compute our Fourier series, we'll rely on integration. And note that all these integral formulae, you're integrating on a symmetric interval, minus L to positive L, okay? Now, that's a very good thing because sometimes we can simplify these integrals. For example, if we have an odd or an even function, an integrand inside our integral. So that's one thing we always look for in integration when we're calculating these Fourier coefficients. Look for odd and even integrands, okay? And I'll talk about that a bit more. You may have forgotten what odd and even functions are, but we'll look at that in a minute. Now also, sometimes you don't have this 2L here, you just have L, so you can combine these two, and you actually put the 2 up there, so it's a naught on 2. It doesn't change anything. It's still the same formulas, the same Fourier series. Okay, so don't be confused if you see a Fourier series with a naught on 2 there, and that little 2 just missing. Okay, it's the same series. All right, so let's have a look at a simple example. I'm going to do 184. Find the Fourier series of the function f given by f of x equals x for x between minus pi and pi, with f of pi defined to be 0. And f is periodic with period 2 pi. And then we're asked to sketch the graph of some of the partial sums of our Fourier series. And we're also asked to draw f on the same diagram. So I'm going to go through that step by step, and when I move on to 185, I'll go a little quicker. So let's have a look at that. All right, so a good thing that I like to do is actually just sketch the function first before I do any integration, because I can immediately determine whether the function's odd or even or neither. So I've got a function of one variable. It's defined as x for x strictly between minus pi and pi. And it's also defined to be 0 at the point x equals pi. Now we're also told that our function is periodic with period 2 pi. Can someone get that? There's actually a note on the door. Just go around to the other. I think the door's broken actually. Oh, hello. That's okay. So I'm going to draw a sketch of this curve. Now, in first year, you would have seen how to sketch these kind of periodic functions, okay? But it's always good to remember. Now, in terms of our Fourier formulae, this big L is, remember, is half the period, and we're told the period's 2 pi. So the big L here will just be pi. Okay, so let's draw the function. Now, the way I do it is I basically draw the graph of x on this interval and put in this point as well. And then I'm going to copy and paste that graph and just move it around a bit. So let's say this is pi, this is minus pi, this is pi, this is minus pi. So at x equals pi, the value is 0. So that's one part of my curve. So all I do now is I take that, I copy it and I paste it. I copy it and I paste it. Essentially, I'm just moving it 2 pi units to the right and to the left. Okay, so essentially, I'm just drawing the same graph, just moved along. Okay, it's not a perfect graph, but you get the idea. Okay, so our function, is it an odd function or an even function? Well, it's odd. Now, there's a couple of ways of describing an odd function. I like to do it graphically. Essentially, if you rotate the whole curve 180 degrees around the origin, it should give you the curve that you started with. Okay, so that's the way I remember odd functions. Rotate the whole curve 180 degrees, see if you get the same curve that you started with. All right? Now, to put this in a slightly more general context, this is the algebraic sort of identity for odd functions. Now, to give you an idea of some basic odd function, think of the curve sine of x. That curve is, that function is an odd function. Now, you may have also heard of even functions. Even functions satisfy this type of identity for all x. With even functions, you've got a reflection in the y-axis. So, if I move x units to the right and x units to the left, then the value of my function is the same. And cosine is a very well-known even function. But I don't like to dwell on that too much. I just do it graphically. Okay. Well, so what? Well, note that our f is an odd function. Okay, well, the reason that's important is because, firstly, if f's odd, I know that my a0 is going to be 0, because when I integrate an odd function on a symmetric interval, the answer is always 0. Okay, to give you an idea of why that's true, suppose this is my function here. This is an odd function, and I'm integrating from, say, minus a to a. See, that area is going to cancel out that area. That area is going to cancel out that area. So the total value of the integral is going to be 0. Now, for even functions, you've got two lots of identical area here. So instead of integrating from minus a to a, what you do is you just integrate from 0 to a and double the integral. Why would you want to do that? Well, 0 is usually an easier number to work with than minus a, and also the function may be simplified. Now up here I've got f is continuous. Well, it can be piecewise continuous or just integrable. Anyway, let's get back to our example. To compute the Fourier series of f, which I'm going to denote by the following. I'm going to denote it by big S f of x. We compute the coefficients a0, an, and bn. Okay? Now, we can get each of those from our little table down here, and what we want to do is simplify as much as possible. Now, a0 is just, okay, I'm replacing big L with pi. Oops, that's a minus pi down there. X is an odd function, and I'm integrating over a symmetric interval. So this is 0. Okay? So this is from minus pi to pi. Now, what about a sub n? That's a little trickier. Here I've got a product of f of x with cosine. Now, cosine's an even function. Our f of x is an odd function. So what happens if I multiply an odd function with an even function? Anyone know what kind of function I get? An odd function, right. Good. So I can cancel off those pi's. And I've got an odd function times an even function. So the product gives me an odd function. Okay, so here I'm integrating again an odd function over a symmetric interval. I just get 0. No calculations required. It's pretty good. Okay, so the last thing we need to do is calculate our b sub n's. Now, b sub n's, just going up here, replacing big L with pi. Cancel, cancel. Okay, so now I've got an odd function times an odd function. So what's the product of an odd function and an odd function? Anyone remember? Odd times odd. Even, yes. Thank you. Even. So what does that mean? Well, it means I can integrate from 0 to pi and double the integral. Now, it doesn't actually simplify the function any bit here, but sometimes it does, okay? Now, here we're faced with the integral of a product. So I just integrated this by parts. So let's have a look at that. Okay, so I'm just going to integrate by parts, and I'm going to carefully explain this because my experience is students still have some trouble with integration by parts when they're doing Fourier series. Okay, so for integration by parts, I want to choose one part of my integrand to be u and the other part to be v dash or v prime. Can anyone suggest how I might choose u out of this product of x and sine nx? Yeah, so choose, say, u equal x and v prime equals sine nx. Why would I choose u equal x though? That's right. A good starting point with your choice is let u equal x in this case. When we differentiate, I get a simpler function. If I differentiate x, I get a simpler function, 1. Now, that will help you a lot of times. It's not foolproof, but it will help you a lot of times. So, let u equal x and let v prime equal sine nx. Now, the integration by parts formula requires 4 things, of course: u, v dash, u dash, and v. So once I have these two, I can calculate u dash. And to get v, of course, I'm just integrating sine nx. Remember, I'm imagining n's a constant here. So when I integrate sine nx, I'm going to end up with something like minus cosine nx. But when I differentiate this, I don't quite get sine nx. So I have to multiply by this factor of 1 on n to patch things up. Okay, so let's apply my integration by parts formula and see how we go. Now remember, integration by parts is just the following formula. Well, I've got 2 here, so I'll bring that 2 out the front. All right. It's going to be u times v, which is just that times that, minus the product of the integral of the product that we just thought up, these 2 functions. So it's going to be the integral of this times this, which is just there we go. Okay, so now I can integrate this and, of course, plug these things in here. So when I plug in x equals pi, I'm going to get the following. When I plug in x equals 0, I'm going to get 0 here, so there's no other term to worry about. So let's integrate cosine nx. Okay, the negative and the negative is going to give us a positive. When I integrate that, I'm going to get something like sine nx. But just like up here, I have to divide through by another factor of n. So I'm going to get something like this. Okay. So now that pi is going to cancel out with that. And when I sub in x equals 0, the whole thing's going to go to 0. And I sub in x equals pi, I'll get something like this. Okay. Now, the question is, can I simplify these expressions? And the answer is yes, you can. Remember, n's a natural number here, right? So cos n pi, cos of a multiple of pi. Let's have a look at that. Well, actually, it's a little bit hard. Let's do the sine n pi first. Sine of 0, sine of pi, sine of 2 pi, sine of 3 pi, they're all 0, right? So this is just 0 for each n, each integer n, or natural number. What about cosine n pi? Well, that oscillates. It goes positive 1, negative 1, positive 1, negative 1, positive 1, right? So can anyone remember, how can I write cosine n pi compactly? Right, plus or minus 1? Even better than that, though. That's it. Cos n pi minus 1 all to the n. That covers the case n equals 1 and the value equals 1 and the value equals minus 1. So this now is my bn's for n equals 1, 2, blah, 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 blah. Okay, I'm already there, almost there now. Let's quickly have a look at what we've calculated. The a naught is 0. All the a n's are 0. The b n's are given here. Let's put them into my Fourier series and just write them out. So I'll replace big L with pi here. So I'm going to get some cancellation. I'll replace a naught with 0, a n with 0, and b n with the thing I just calculated. 0, this is going to be 0, so these are going to disappear. And I'm only going to be left with a sum involving sine. So S f of x, which is the way I'm going to denote my series, well, I know the a naughts and the a n's are 0. So this is the general type of series I'll get. So let's replace b sub n with this. Replace big L with pi, so we get a bit of cancellation. And here we are. Okay, it looks a bit messy, but the second part of the question actually asks us to just define this function in this way, where b1 and b2 are just the coefficients for n equals 1 and n equals 2. Sketch this graph and draw the original function on the same diagram. So let's calculate this function defined in the following way. So it's like a partial sum of my Fourier series. Okay, so what's b sub 1 going to be? I've put n equals 1 in here. I'm going to get minus 2 times minus 1. So I'll get 2. And if I put in n equals 2 in here, I'm going to get negative 1. Okay, so here's my general Fourier series, and here's just a partial sum of that. All right, so it's asked us to sketch the function. Here's one I've created earlier. Okay, so that is the function f sub 2, the partial sum. And then it asks you to sketch the function with f sub 2. So again, that's one I've sort of half done with Maple and half done by hand. Now you can see a couple of things from this picture. Firstly, it's an okay approximation. So the red curve is an okay approximation to the green curve, but it's not great. If you kept adding, maybe go up to the 10th term, the 10th partial sum of your Fourier series, you would get a tighter and tighter wrapping around the green curve. Okay, and you get this crazy situation where you've got this really tight wrap and then this almost instantaneous jump down to the start of this part of the green curve. Okay, so a couple of things to observe. With a Fourier series, what you're doing is approximating a discontinuous function with a continuous function. That's kind of cool. Okay, and what happens is these sort of, as you take more and more partial sums, you get a really tight grip in the middle, and then at the edges, you get it's like it starts bouncing up and down again. It's almost like it's getting prepared to do this crazy jump down here. So that's another important property. Okay, here's the theorem. If you've got piecewise continuity of f and f prime, then f's equal to its Fourier series at all points where f's continuous. And where you have a point of discontinuity, the Fourier series just converges to the average of these left and right hand limits. Okay, but we'll have a look at that in the next question. Any questions for that one? Okay. Now, if I was in the exam and I was doing a question like this, I probably wouldn't even write out these things. Okay. If you can just write down, little f is odd, therefore a sub naught 0 and all the a sub n's are 0. That's fine by me. You don't have to go into this explanation, but I've just done it so we're clear. Okay. Now, here I've got odd times even equals odd times odd equals even. What about an even times an even function? What would that give you? Even, right. So the way I remember it, if you've got the same type of function multiplied together, it always gives you an even function. Anything else gives you an odd function. Say if you've got a mixed product, it's an odd function. Okay? Okay. Now I'm going to go through this one a little quicker. 185. Find the Fourier series for this function here. You're asked to determine the value that the Fourier series converges to at these points. Sketch the graph of the function to which the Fourier series converges to on this interval, and use the value x equals pi on 2 to formulate some value of a infinite series. Okay, so who's done 185? Anyone? Anyone? Okay, it's a good one. I've seen that on lots of tests. So I'm going to go through this a little quicker than the previous one. So we've got a function that's defined in the following way. It's periodic with period 2 pi. Let's draw the function, okay? So the way I'm going to do it, I'm going to draw the function on the interval minus pi to pi first, and then I'll take that and copy and paste it. So okay, here's my function on the interval minus pi to pi. So let's copy it and paste it. Copy it and paste it. And I'll just draw it on the interval minus 3 pi to 3 pi. Okay, so okay, I'll just continue this over here. Okay, now, not a very good drawing, but hopefully you can get the idea. The question is this function odd, even, or neither? Is it odd, even, or neither? It's neither even nor odd. Okay, so this is slightly annoying because we can't, when we want to calculate our Fourier coefficients, we can't just, use the odd, even simplification. Can anyone suggest how we might make it? Oh, hang on, I think I've. Yes. Yes, now you're talking. Yes, absolutely. Brilliant. Is that how you did it? Or you're just looking at it now? Yep. Okay. Now, one way is to move everything down half a unit. Then it will be an odd function. So what I'm going to do, I'm going to be a bit sneaky, and this is another good time-saving technique. I'm going to move the whole curve down half a unit. I'm going to calculate the Fourier coefficients for that, and the Fourier series, and then I'm just going to add 1/2 to the series that I calculate, because I'll shift the series back up then. Okay? Cool, very cool. So our f is neither even nor odd. We shift it down. The y-axis, 1/2 units to form an odd function. Okay, so we're going to consider a new function, g. that is basically just this function shifted down half a unit and the same periodicity. So it's going to be a half and minus a half. Okay. Now, this is the best thing. If I want to calculate the Fourier coefficients for my g, and g is an odd function, a naught 0, a n's a 0. That's it. That's all I have to do. Okay? All right, so let's a naught is 0. All the ANs are 0 as well, since G is odd. And again, since G is odd, the B sub n's are just twice the integral from this formula. Again, big L's pi here. Okay. Now, if I'm integrating from 0 to pi, what is the value of my function g on that interval? Well, it's a half. It's not negative a half, it's a half. So this is what I'm going to get. So now all I need to do is calculate this. Obviously the 2 is going to cancel. So if I integrate sine nx, I'm going to get something like cosine nx. But then I have to adjust for that n, so I get this. So now if I substitute in, well, when I sub in pi, I'm going to get cos n pi. And when I sub in 0, I'm just going to get cos of 0, which is 1. Now, similar to the previous, I can just simplify my cosine n pi. Now, what will this simplify down to? We can go a step further and simplify this even more. If n's even, minus 1 to the n is going to be positive 1. So I'm going to get positive 1 minus 1. If n's odd, well, this thing in the big brackets is going to be minus 2. So when I multiply through with here, I'll get 2 on n pi. So I've got a sort of a strange setup for my b sub n's here, but it's actually going to it's going to help us out, so don't worry. Now, let's write out the Fourier series for my shifted function g. I've shifted it a half unit. What I'll do is once I have my Fourier series for g, I'll add a half to the Fourier series, so that'll put it back in the right place. So my Fourier series for g, essentially I just go up here. I know my a naught 0, I know my a n's are 0, and my b n's I'll just put that in as we go. Now I'm only going to sum over the odd values of n here. Why am I doing that? Well, because for all the even values of n, I'm just adding up 0, 0, 0, 0, 0, 0. So that's, you're not contributing anything. Now you may not want to sum over the odd values of n. You may want to put it in a more standard manner. So let's replace n with 2k minus 1. Now, if k is, let's say, a natural number, 2k minus 1 is always odd. So that's the idea. So we're going to sum over k equals 1, 2, 3, etc. and replace n in our sum and with 2k minus 1. Okay, now we're almost done. We've got our Fourier series for g. Let's just add 1/2 to it, and we will get our Fourier series for our original unshifted function. So I'll put the 2 on pi out the front. Oh, okay. With these kinds of problems, you always want to see if you can simplify the calculations. As long as you write down, oh, well, I've got an odd function or an even function or something like that in your exam, I don't think you'll be penalised, okay? I mean, I certainly wouldn't penalise you. I think that's a smart way of doing it. Okay, so that's the first part. To what value does the series converge at the point x equals 0 and the point x equals 2 pi? Well, let's go and have a look at our graph. At x equals 0, so this is the graph of f here. Is the function f continuous at x equals 0? Yes or no? No. So by the theorem that I put up before about convergence, at points of discontinuity, the Fourier series converges to the average of these two limits. Okay, so the left-hand limit as we approach 0 is 0. The right-hand limit as we approach 1 from the right is 1. So what's the average of 1 plus 0? A half. Okay? So at the point x equals 0, the Fourier series converges to 1/2. What about at the point x equals 2 pi, which is there? Again, we have a point of discontinuity. So the Fourier series would converge to 1/2 there. Okay? So this is part B now. Oh, hang on. Have they asked us to do that there? To what value does the series converge to? Yes. Okay. Since f of x is not continuous at x equals 0, we have the Fourier series converging to the average of the left-hand and the right-hand limit. Okay, so similarly, all right. Now part C, sketch the graph of the function to which the Fourier series converges. Okay, so we're not sketching the function now, we're sketching the original function, we're sketching the function to which the Fourier series converges to. Okay, so it's basically the same graph except you just shift the points. So instead of having up there to be there, move that point up to there, up to 1/2. So at any points of discontinuity, you would sort of shift the points to be 1/2. Okay, so Okay, so here are all our points of continuity. The theorem that I put up before says at points of continuity, the Fourier series and the original function they have the same value. Okay, it's only at points of discontinuity that you have something a little bit different. So at the points of discontinuity, the value of the Fourier series is just the average of the left-hand and the right-hand limits. Okay, well, why is that important? Well, part D asks you to use the value x equals pi on 2 to find a series which converges to pi on 4. Now, Fourier series can be used to evaluate the value of an infinite series. Think back to first year, we saw series, we were interested in whether a series converged or diverged, right? We had all these tests. Now, Fourier series actually can give us the opportunity to find the value of an infinite series, and this is hugely difficult otherwise. Okay, so let's have a look at D. Let's have a look at our original function. Let's say x equals pi on 2, which is here. What's the value of our original function x equals pi on 2? It's 1. And in particular, the function's continuous at x equals pi on 2. So f of pi on 2 is just 1. And because we have continuity, we know that the value of the Fourier series at pi on 2 is equal to the value of the function at pi on 2. So what I'm going to do is go back to my Fourier series, plug in x equals pi on 2, so it'll just be this, and set the whole thing equal to positive 1. Then I'm going to simplify it. Okay. So now I'm running out of time now, so I'm just going to quickly finish this off. I can simplify sine of an odd multiple of pi on 2. It's actually going to be the following. And I'll get you to verify this or ask yourself why it's true. I can replace sine of this with this. So all I need to do now is take the half to the other side, multiply through by pi on 2. The right-hand side is going to give us pi on 4. So it looks like I've got my series. But what's this left-hand side? Well, let's write out some of the terms. Well, the first term is going to be 1. The second term is going to be minus 1/3, plus 1/5, minus 1/7, plus 1/9, etc. This is a special series. Anybody recognise it? It's an alternating series, and it's attributed in some parts of the world to James Gregory, who was an astronomer and a mathematician. So this now shows you how you can use Fourier series to get the value of infinite series, which is very, very, very difficult. Very difficult.